And we'll do kind of the same thing with biomolecules. We'll look at amino acids, we'll look at peptides, we'll look at proteins, nucleic acids, whatever. Just kind of a general sort of picture show, though. On the exam, you are not going to be asked to do complicated things like naming organic compounds. We'll save that for organic. But we're going to go through it just so that you get a feel for how this stuff is done. This on the screen here, this represents the molecule ethene. It's a carbon-carbon double bond in here. And this is what's called the pi cloud, above and below the carbon skeleton. So we'll talk about that in just a little bit. The word valence in chemistry basically describes how many bonds an atom will form in its neutral ground state. Water will form 2 bonds, as in water, and the valence is 2. Nitrogen is 3. Boron is also 3. Remember, nitrogen and boron are different because nitrogen will have the pair of electrons, and boron does not have 8 electrons, poor guy. Carbon, however, is 4. Carbon forms 4 bonds. Now, way back in chapter 1-ish, we looked at electron configuration. Carbon has an atomic number of 6, and it's in the second period here, so right there. That means that the first period electrons are filled, the S is going to be filled, and we're going to have 2 in our P block. So it's going to look like this. The 1s, that's this guy, up there with hydrogen and helium, that's all filled. The 2s, that's here with lithium and beryllium, that's filled. And now we have 2 electrons over here in the P's, right there, 1, 2, and so it looks like that. Now, if we put this all together, it's going to look like this: 1s2, 2s2, and 2p2. All right, now we said that carbon has a valence of 4. If you just kind of looked at this, we have 2 unpaired electrons. We know we need unpaired electrons to form bonds. In order to form 4 bonds, what we have to do is take one of these electrons from in here and move it out. This gives us 4 unpaired electrons, and so we can form 4 bonds to our basic carbon. The simplest carbon compound is methane. We'll talk about how it's named that way. 1 carbon, 4 hydrogens. This is what it looks like. The geometry is tetrahedral. That means that the carbon is raised up off the plane of these 3 hydrogens, so it's raised up here a bit. And all of these angles and all the bond lengths are identical. They're all 109.5. If we take the ball and stick model out of this, methane looks like this. And again, with this one, you can see clearly that the carbon atom is in the middle of this little pyramid-shaped thing called a tetrahedron. When we have carbon compounds that have tetrahedral geometry this way, we say that they are hybridized orbitals. Now, hybridized orbitals simply means that we, if you remember what we did, we needed 4 unpaired electrons, right? We took 1 from an S and put it in the P, so we have an S and 3 electrons in P's. So we call this an sp3 hybrid. We'll see that there are other hybrids you can make, sp2, sp squared, or sp. but we'll talk about those in just a bit. When you have a compound that is made up of nothing but sp3 carbon atoms connected in any way, we refer to this as an alkane. Now, in organic chemistry, we do what are called functional groups. Functional groups are really useful in organic because all of the compounds within that functional group will share very similar reactions. So if you remember that a certain functional group reacts in a certain way, then that basically goes for most compounds in that group. And there's almost an infinite number of compounds. So it's a very nice way to categorize organic compounds by their group. Well, the functional group here is alkane. This group has 3 carbons. This molecule has 3 carbons. Each of these are sp3 carbons. And you know that because they all have 4 bonds. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And they're all single bonds. If we looked at this in a 3D model, it would look something like this. Again, all of these carbons are tetrahedral. All of these bond angles everywhere are 109. And you'll note that because of the 109-degree bond angle, that this kind of goes a zook-zook sort of thing. When we learn to draw organic structures, we'll see that the zigzag, the up and down, is basically the way we start. And that mimics the actual geometry of the sp3 carbon bonds. Now this is what we call a straight chain. It has 3 carbons, they're connected end to end, blah, blah, blah. We can also have an alkane, something like this. Here's our 4-carbon main chain, that's called the parent. And here we've stuck a 1-carbon chain off to the side. This is a branched chain alkane. 3D, it would look like this. Here's our 1, 2, 3, 4-carbon parent. The longest chain is the parent. And here on the 2nd carbon end, we have a CH3 sticking up. Again, all of these are sp3 carbons. They're all tetrahedral. And all of these bond angles everywhere are 109. Any questions? If you look at an alkane, here the one we looked at with a 3-carbon parent chain. Here was our 4-carbon parent chain with a CH3 as a side chain. There's a pattern as to the general molecular formula. Here we have 3 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. An alkane will have a general formula of CnH2n plus 2. N is the number of carbons, so we have 3. So 2 times 3 is 6, plus 2 is 8. This guy has a formula of C3H8 with N up here equal to 3. This guy down here, we have 1, 2, 3, 4, 5 carbons. So N is going to be 5. Our hydrogens, if N is 5, 2 times 5 is 10, plus 2 more is 12. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. An alkane will always, regardless of how branched it is, will always have a straight chain alkane. Will always have CnH2n plus 2. Now we'll see that we can do things with carbon compounds. We can form rings. When we do that, we get a different functional group called a cycloalkane that differs from this. But for a straight chain alkane, this is always true. Now, if we want to name these things, what you want to do is to simply look for the longest continuous chain of carbon atoms. Like I said, that's the parent. If we have one carbon, that's the methane that we looked at, meth is our prefix, A and E stands for alkane. So meth means 1, eth means 2, prop is 3, but is 4, pent is 5, hex is 6, hept is 7, etc., etc. The fact that all these names have A and E on the end tell you that they're simple straight chain alkanes. So if we have down here, well, let's try something I can pronounce. How about dodecane? If we had dodecane, we would simply have a chain of 12 carbon atoms. 2 times 12 is 24, plus 2 is 26, and this is C12H26. So for the simple straight chains, the naming is very, very simple. Now, carbon compounds can be very, very complex. When we looked at a branched chain a little bit ago, we said there was a CH3 sticking out. This is called a radical of some sort. It's a one, the CH3 group was a 1 carbon group. And we're going to use the same basic nomenclature we did before. 1 carbon we said was methane. 1 carbon attached to something is methyl, YL. YL tells you it's attached. 2 carbons, like this, CH2, CH3. 2 carbons is an F. 2 carbon attached is an ethyl. This also works for other functional groups. Something with an OH in it is called an alcohol. This has a 1 carbon chain, so it's methyl alcohol. This is an amino group, it's our nitrogen. Again, 1 carbon chain, this is methyl amine. So the same basic scheme of nomenclature is used for all of them. Again, if we have methane, here's 1 hydrogen off, that's a methyl. 2 carbons is an ethyl, 3 is a propyl, 4 is a butyl, 5 is a pentyl, etc., etc. So this is how we can name branches on our carbon compounds. Any questions? All right, how do you represent carbon compounds? These are all ball and stick models. The neat thing about carbon, the thing that makes organic chemistry so amazing, is that there's just a huge, huge number, almost an infinite number, of possible carbon compounds. Up here we have a simple branch chain alkane. We have a parent chain of 1, 2, 3, 4, 5 carbons, and we have a methyl group, a single CH3 sticking up here on our 2nd carbon. Here we have 6 carbons, but it's in a ring. This is called a cycloalkane. Again, all of these bond angles are 109, but because it's in a ring, it's not a CnH2n plus 2. It actually turns out to be a CnH2n. We're not going to talk about that. This is a polycyclic compound. Now it's a little tough to see here, but we've actually got one ring here. 1, 2, 3, 4, 5, 6. Another ring here. 1, 2, 3, 4, 5, 6. So these are two 6-membered rings kind of fused together. Polycyclic is called. We can also have organic compounds with not just single bonds, but double bonds. This is morphine here. This features carbon-carbon double bonds, those guys. We also have oxygen atoms. Remember, oxygen in models is red. Nitrogen is blue. So in morphine, we've got a 6-membered ring up here with an OH. There's another oxygen going down to another ring in the background, and another ring here with a nitrogen atom. And here's a CH3 sticking out the side. This is glucose. We've seen glucose several times. Every carbon in glucose is bonded to an oxygen, and most of these are bonded to OH groups. This one is an oxygen bridging 2 carbons. Again, a 6-membered ring, a CH2, and an OH. Very, very complex structures are possible. When we speak of compounds like this, we refer to these guys, the oxygen and the nitrogen, as heteroatoms. Hetero because they're not carbon. In organic chemistry, carbon is king. Everything else is something different. Carbon, hydrogen, and then you have the other guys. Carbon can form bonds to basically any other element. It's amazing. Between carbon and water, carbon compounds and water, that's why life can exist. Complexity is possible with these structures. All right, we've shown these things as ball and stick. Ball and stick is a nice thing. If you take and you get rid of all the little balls, you get what's called a Dryden model. Here you simply show the carbons and these are little hydrogens sticking out, same molecule. And this guy's a space filling model. These are all on the same scale, so this is what these things really look like in space. This is probably the easiest to interpret. And also, we'll see, the easiest to draw. If we looked at this compound, we have 4 carbons in our parent chain. 1, 2, 3, 4. Again, it's a zigzag, isn't it? We could write the simple molecular formula, but that tells us darn near nothing. C4H10. What in the world could that be? This is called a condensed structure. This is what you'll see mostly in textbooks. In a condensed structure, we simply say we have a CH3, then a CH2, another CH2, and a CH3. It's nice because it tells us the connectivity. It doesn't tell us much about the geometry, but at least we know the connectivity of the molecule. This is called a Kekulé structure. Kekulé is a famous guy in organic chemistry. We're not going to talk about him. You have to take organic to do the Kekulé stories. But Kekulé decided that we could take and just put in dash bonds on all of our carbons and draw a structure like that. And finally, this is the ultimate simplification for all of it. This is how we will typically draw a real organic compound if you were taking organic on an exam or something like that. This is called a truncated line. So it goes out and stops. When you see that in an organic compound, you know that that is a CH3 group. This line that goes up and stops It's the same thing as our CH3 right here. Every time we see a vertex in our zigzag, again, we're going to draw these as zigzags, we know that the zigzag represents a CH2. So we look at this and we say, in this structural drawing, we have a CH3, a CH2, CH2, and another CH3. Now, that's the way it's supposed to work. However, you will see lots and lots of different representations. Here's our calculate structure for our 4-carbon alkane. And again, we have 1, 2, 3, 4 carbons in the alkane. Sometimes, to help you, people will put CH3s on the end, just to help you remember that the truncated line is a CH3. Now, if you look at this, this one kind of makes sense, but this guy up here, you look at it and say, well, wait a minute, where is this bond going to? It's not going to the hydrogen for sure. So to be a little more correct, quite often people will reverse it. And you'll have H3C and CH3 on the two ends. On many, many organic structures that you'll see in textbooks and everywhere else, you'll get an absolute mix of all of these things. So you just have to, just deal with it. Bottom line on a simple line drawing, just remember the truncated line, this guy here, that point, represents a CH3. Vertex represents a CH2. Any questions?
Do we use this in daily life?
Hmm?
Do we use any of that in daily life?
Oh, you use everything. You're made up of this.
It's like, nope.
All right, here's our line drawing, and this guy I put methyl groups on the end, oriented properly just to help you. Another representation that you'll see, people will sometimes take the moral equivalent of a line drawing and they'll turn it so it has perspective. When they do that, you get what's called a sawhorse projection. And this is what I mean. You'll see every possible permutation of organic structures. This is obviously a CH3, it's this one. This guy's a CH2, well here it is. We just didn't show the carbon. This guy's in front, and in back here, we have our CH2 and another CH3, called a sawhorse. If we take this sawhorse and we turn it so that we look straight down this bond, this is in front, that's in back, straight down the bond, we get what's called a Newman projection. In a Newman projection, this guy here is this one, is the front carbon, and we make the back carbon a little ball. We do that just so we know it's the back carbon. It's the same exact structure. CH3, CH2, here's a C, H2, and another CH3. This is a little movie that I made showing it. Again, this is a drying bottle. And what we're going to do in this is rotate this so this comes forward, this goes back, and we're going to make a sawhorse first. Then we're going to take the sawhorse and rotate it so this guy's in front and that's in back. So there's our drying model. Here's our sawhorse. And finally, here's our big atom in back. This was the one in front. It's just a simple rotation and perspective thing. Lots of times in organic chemistry, you care about orientation of groups relative to each other. And Sawhorse projections, Newman projections can be very useful at trying to figure that out. All right, let's go ahead and take some structures and just practice making line drawings. All right, nice simple exercise. We have, first of all, a condensed structure. What we want to do when we draw a line drawing is, number one, determine the longest continuous carbon chain. And that's going to be, starting down here, 1 carbon, 2, 3, 4, 5. Now these two methyl groups, shown in parentheses, are attached here to carbon number 2. Carbon number 2 has no hydrogens, does it? Carbon 3 does. Instead of hydrogens, carbon 2 is 2 methyl groups. So the first thing you would do is just to sit down and do a zigzag. And you can try this, play along. Do a zigzag with 5 carbon atoms. Remember, both ends count, including the zigs and the zags in the middle. So we would simply do this. 1, 2, 3, 4, 5 carbons. And that's our carbons numbered 1, 2, 3, 4, and 5. Both ends are CH3s. These guys are CH2s. Now the other thing we know about this molecule is that on carbon 2, we have 2 methyl groups. That's 2 one-carbon chains. How do we show a methyl group? Just as a line that goes up and stops. Truncated line. So we would do it this way. That's 1 methyl group, and that's the other. This is a line drawing corresponding to this guy. Yeah.
So the vertical line is probably the carbon CH3, correct?
Right, that's the carbons that are attached to carbon 2. Remember, a truncated line is a CH3.
Why does it go past the equator, so to speak, of the horizontal line? Why doesn't it just stop at the
Oh, stop up here? Oh, well, they should all be the same length.
Because
Because
you see how
all,
vertical it goes on top and bottom, at the horizontal line, and then the vertical line is on top. And then
right, now, this does not reflect the accurate 3D geometry. Because this is going to be a tetrahedral carbon, one will be forward, one will be back, etc. But that gets a little more complicated.
Yeah, a little complicated more.
Our next guy, we have 6 carbons in a ring. We'll call this cyclohexane. If you notice, all of these are CH2s, aren't they? How do we show a CH2 in a line drawing? Simply as a vertex, right?
Yes.
Every vertex is a CH2. So what is this guy? 6 vertices in a ring.
Oh my God.
Isn't that cute? Every one of these is a simple CH2. You can see it goes up, down, right around the ring. This is actually what we call chair cyclohexane. If you have a vivid imagination, you can imagine this as kind of like a lawn chair, sitting back and relaxing. You know, goes down, goes back, here's the back of the chair, there's the foot. This is chair cyclohexane. There's also a boat cyclohexane. We won't do that. Now let's look at this guy. This is a Newman projection, isn't it? Our task here is to figure out our longest chain. Okay? So, if we look at this, let's start up here somewhere. Doesn't matter where. We'll start at one end. How many carbons in our longest chain? We have 1, 2. This is a carbon, right? That's number 3. That's the front carbon. Now this guy is the back carbon, so that's carbon 4. Then it's attached to carbon 5 and carbon 6. So we have a 6-carbon parent chain. So we're going to draw our zigzag like this with 6 atoms in it.
That CH2 represents the one that's in the back.
This right here, this is the back atom. It has a hydrogen, a methyl group, and an ethyl 2-carbon chain. So counting 1, 2, front carbon is 3, back carbon is 4, 5, 6.
What about the bottom ones?
Oh, those are side chains. They're attached to our parent.
Oh my God.
First thing you do is find the longest, and it's 6.
How would I know it's attached to the side?
Well, because again, we'll look at this in just a second. We'll turn this into a sawhorse, and it might be a little clearer. But okay, so let's go down this way. Our front carbon here is the 3rd one in, isn't it? And it's got a CH3 on it. The 4th carbon, that's the back guy, also has a CH3. So we simply need to go over here and say our 3rd carbon in, 1, 2, 3, has a CH3, and so does carbon 4. We have a 1, 2, 3, 4, 5, 6 carbon parent, and 2 methyl groups, 1 on the 3rd and 1 on the 4th. Now let's just take this and untangle it a little bit, see if it makes it simpler. This is the answer we just gave, right? If we take this thing and turn it into a sawhorse, this is what we get. Here's our front carbon, CH3, CH2, that's those two. There's a front carbon. Then we go to the back carbon here, which is attached to a CH2, CH3 this way. Here's our 6-carbon chain. 3rd carbon in has a methyl. 4th carbon in has another methyl.
So what about those H's?
Oh, they're all there. Remember, every vertex is a CH2. This guy, of course, is a CH. So is that. Because every carbon must have 4. A valence of 4. If you don't see it, it's a hydrogen.
So the hydrogens are missing?
I'm sorry, the hydrogen.
The hydrogen is not represented.
Right,
up
we
there?
do not, in a line drawing, we do not show the hydrogen.
And is this going to be on the test? Because
All right, let's take this up to one more level. If I told you to draw a 1, 2, 3, 4, 5 carbon chain with a 2-carbon side chain, you could do this, right? But all of these are single bonds. And one of the neat things about single bonds is that they spin. They spin about 10 to the 6 times per second. So it might look like this at one instant in time, but we could rotate around here, so we're pointing this way, not that way. We could rotate so we're pointing down, or up, whatever. This is very clearly shown in what we'll see on the next slide. These are called conformational isomers. And because they change 1,000,000 times a second, we ignore it. We say that these are the same compound. So if you were to draw a 6-carbon parent with a 2-carbon side chain and you drew it like this, that's absolutely correct. Any way you want to draw it is correct. Here's our movie. These guys are just moving, they're spinning, they're going back and forth, up and down, all around. Any of those are acceptable conformations. They're all conformational isomers. Here's another way to look at it. Here we have 3 alkanes. They're all 5-carbon chains with a 1-carbon side chain. Up here, our 5-carbon chain looks like that, and here's our side chain. Here, look like this. Now we put the side chain on this side. Here, our 5-carbon chain looks like this. These are all perfectly acceptable structures. They've changed so fast that we really don't bother thinking about them. All right, enough of this calling things 5 chains and whatever. Let's see how organic chemists actually name compounds. This is kind of an interesting exercise, I think. This is called IUPAC nomenclature, International Union of Pure and Applied Chemistry. Big honking set of rules on how to name virtually every chemical compound that there is. First thing you do, rule number 1, you look at your compound and you find the longest continuous chain. So look at these 3, I think they're on your handout, and just identify, draw over it, the longest continuous chain. For our first one, it's very simple because there's only one chain, isn't there? There's no branch. We simply start down here, and we go 1, 2, 3, 4, 5, 6, 6-carbon chain. Our next one here, we're looking for the longest. If we just follow the horizontal zigzag, we'd have 1, 2, 3, 4, 5. But if we turn up here, we have 1, 2, 3, 4, 5, 6, a 6-carbon parent chain. This guy, we can do 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Oh my gosh, there are 2 of them. We'll see in a bit that this chain here is going to be preferred. 1, 2, 3, 4, 5, 6, 7. Oh, that was 7. That's why it's preferred. Again, it doesn't matter how it goes. You simply look and you find the longest continuous chain.
So the ends count too.
Yep. All right. Once you identify the chain, that's going to be your parent. If it's 5 carbons, you remember that 5 is pent. So it's a pentate. Now, if there's things attached to it, it's going to be a substituted pentate. So let's look at this guy. We're going to, with a chain, you're going to start numbering at one end or the other, aren't you? What you want to do is always number your chain closest to the first side chain. So if we look at this guy, we can do 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. Two possible ones. Let's just draw 1 and 2. These are identical, aren't they? Here we've just gone up, and here we've gone down. They're both 7-carbon parents. Now we want to make carbon number 1 down here closest to our first side chain. That's our substituent. And then we're going to build our name based on this. There is one tiebreaker here, however. If we have 2 chains that are both the same length, IUPAC tells us that we want to choose the chain with the greatest number of substituents. So if we look at this guy, here we have 2 side chains going up, right? On this one, right here, we'd only have 1. This is the bad choice, and this is our good one. We would start numbering here, because it's closest to our first substituent. 1, 2, 3, 4, 5, 6, 7. 7 is hept. So this is a heptane. All right, let's take this guy. Here we're going to have, well, both of these, this carbon has 2 methyl groups attached, right? This one has another methyl group attached. This has a 3-carbon chain attached. When you have more than one substituent attached, all you're going to do is say you have more than one. And we'll do that with a multiplier, di, tri, tetra, whatever. Just like we did in simple nomenclature here. If we look at this, what's our longest chain? Longest chain with the most substituents. Well, we can do 1, 2, 3, 4, 5, 6, 7. Or 1, 2, 3, 4, 5, 6, 7, 8. I think 8 wins. And it looks like that. We'll make this guy carbon number 1 because this first substituent is closest to it. Now let's build a name. Here on carbon number 2, we have 2 methyls, right? And on carbon number 6, we have a 3rd. So to build our name, we say 2, 2, 6, tri, meaning 3 methyls. Next, we look and say, what else is attached? Well, here on carbon 1, 2, 3, 4, we have a 3-carbon side chain. 1, 2, 3. That's a prop, isn't it? That's a propyl. So we have a 4-propyl. And what's our parent? 8 carbons is an octane. So we put it together for a name. Our name is going to begin and be listed alphabetically. The parent is going to come last, as it often does. When we have a multiplier, we ignore the multiplier and just go in here to the group. So this is an M, and that's a P. So the first thing we would write would be our 2,2,6 trimethyl. Now attached to this chain also, we have a propyl group at carbon 4. Going to put a dash in to separate it and say 4-propyl. And finally, with no space at all, we will indicate our parent is simply an octane. 2,2,6-trimethyl 4-propyl octane. Now, if you had the name and you worked backwards, how would you do that? You'd actually start at the end here. You say, okay, I need a chain of 8 carbons. I'm going to call one carbon 1, and on carbon 2, 2, and 6, here, here, and here, I'll put methyl groups. And on carbon 4, I'll put a propyl, that's a 3-carbon side chain. Now our last rule have to do with things like halogens. Halogens have very low priority. We just pretend that they're like hydrogens, except of course they're not. So here, instead of a methyl group, I just put a chlorine on. Okay? So now what do we have in our molecule? On carbon 2, we have 2 methyl groups. So that's a 2,2-dimethyl now. On carbon 4, we still have a propyl group. So that's a 4-propyl. On carbon 6, we have a chloro. And finally, our parent is an octane. Putting it all together, who wins alphabetically? Fluoro wins, absolutely. So it has to come first. Then we're going to get our 2,2-dimethyl. And then we can do our 4-propyl. And finally, we tell the world the parent is an octane.
This is crazy.
So using these very strict sets of rules, you can take every organic molecule and give it a name that you can then work from the name, go back to the absolute structure. It's a very, very good system. Yeah?
You probably have already explained this, but I might have missed it at some point. I didn't know if you have such a diagram, or if you have such a diagram, how do you know whether to, which route to take?
The what? I'm
How
sorry?
do you know which route to take?
Well, you just have to kind of like figure it out. Now, if we went up this way, it'd be 1, 2, 3, 4, 5, 6, 7 carbons. 8's bigger. So that's it, as simple as it could be. 8's bigger. Let's go ahead and name a couple. Now, you know, everybody freaks out whenever I put a Newman projection on, but they're really simple. And, you know, in organic chemistry, they can really be useful. So that's why we stress it early in the course. What you want to do is look at this guy and figure out what the longest chain is. Remember, that's a carbon in front, the big ball's a carbon in the back, right? So here we have 1, 2, the big ball is 3, 4, and 5. If we drew this as a sawhorse, it would look like this. Here's our front carbon, 2 hydrogens, and a methyl. There's our big back carbon here, our CH2, CH3, and another methyl. So what's our longest chain? Looks to me like it's going to be 1, 2, 3, 4, and 5. Now we need to decide who gets carbon number 1. Actually, the methyl group is in the middle of this chain, isn't it? So it doesn't matter. It's a tie. So let's just let this be carbon 1 just for the heck of it. So what's our parent with 5 carbons? It's a pentane. What's attached to carbon 3? A methyl group. So this is going to be a 3-methyl pentane.
Why do you know it's a methyl?
This is our side chain, that's our methyl, right there. Here's our parent, and on carbon 3, we have a methyl. One carbon side chain is a methyl.
Because it's CH3.
Mm-hmm. Look at this guy. Finding the longest chain here is really simple. Doesn't matter which of these CH3s you start with. It's going to be 1, 2, 3, 4. Now you see these little bonds with dashes and a big bold sort of thing? That actually shows what we call stereochemistry in organic. And when you look at this, this is supposed to tell you this is going back away from you. And this is coming towards you. Stereochemistry, again, is a very important aspect of organic. All right, but our main chain here is simply going to be 1, 2, 3, 4. On carbon number 2, we're going to have 2 CH3s, that's 2 methyls. So it's going to be a 2,2 dimethyl. Let's pretend that's our parent. This will be carbon 1, this is carbon 2, 2 methyls on carbon 2, 2,2 dimethyl butane. Bute is our 4-carbon parent, 1, 2, 3, 4. Now, again, I could have made any of these carbons number 1. Doesn't matter, they're all the same. Let's take that here. Let's just show the magic. I just took and ripped a hydrogen off of here and put a chlorine on. Let's see how that changes it. Now we're going to have a chloro and 2 methyls, aren't we? Oh, I put another chloro out here too. How about that? So what do we have in our name here? Remember, we want the first substituent to have the lowest number. So this is going to be carbon 1 right here. It has to be. So the chlorine can be attached to carbon 1. And that's going to make this our parent. So what do we have? We have a 1 chloro and also a 3 chloro. So that would be a 1,3 dichloro, wouldn't it? 1,3 dichloro. And here on carbon 2, we have 2 methyl groups. So it's going to be a 1,3 dichloro, 2,2 dimethyl. And it's a butane.
Why 3 dichloro?
Well, we have 2 of them.
Right.
One here on carbon 1, one here on carbon 3. So it's a 1,3 dichloro.
So it's on 1 and 3.
Right. Let's do it backwards. Go ahead and see if you can take these names. We've done enough now. You can do this. Take these and make a simple structure for me. First one's a butane, so that's 4 carbons in our zigzag. Pick one end, call it carbon 1. On carbon 2, we're going to have 2 methyl groups. That's 2 little lines sticking out. And on carbon 3, we're going to have a 3rd methyl group. So our zigzag looks like this. And I'll let this guy be carbon 1, just because I can. On carbon 2, we have 2 methyl groups. So that's 2 lines coming out of here. On carbon 3, we have another methyl group. So that's another line. 2, 2, 3, trimethyl.
So what if you did the line going one down, one up?
Doesn't matter. Same structure. Remember conformational isomers, it doesn't matter. You can, I always draw a horizontal zigzag because it's easy.
Uh-huh.
You can draw it any way you want.
No, I mean how you put the,
Oh, the methyl groups?
yes.
Well, remember this, these aren't wedgies. We call the others wedgies because they show stereochemistry. So it doesn't matter where you put them.
Okay, so I,
Yep.
like for example,
Any way
I
you want.
could put it one down.
Down and
one
up. Yep,
Okay.
absolutely.
And I could have gone the other way where the other
Sure.
side is one, right?
Of course. This is a hexane. That's 6 carbons in our zigzag. Go ahead and do your zigzag. Six carbon zigzag should look like that. And just for the heck, I'll let this end be carbon 1 this time, just to show I'm being fair. Now, this is 3-ethyl. So if this is carbon 1, carbon 3 is right here. Ethyl is a 2-carbon chain. So we need to stick a 2-carbon chain on here. On carbon 2, down here, we have 2 methyl groups. Putting them all together, 2,2-dimethyl, 3-ethyl hexane. Again, it doesn't matter how you point the little lines. Doesn't matter. As long as you have 2 methyl groups on carbon 2 and an ethyl group on carbon 3. Now, because you know you can draw these structures any way you want, if you're teaching organic and you have like a large class, could you imagine grading an exam where people draw structures because you have to really look at everybody's structure because they're all going to draw it differently.
I have a question.
Sure.
On 3, you have an ethyl.
Ethyl, right here.
Oh,
1,
that's
2.
1. So you have to draw 2.
Right.
Okay.
Ethyl is 2 carbons.
Which is the number that follows.
Uh-huh. This guy is an octane, so you start off with 8 carbons in a row. And decide which end you want to be carbon 1. Now this is hexamethyl. That means we have 6 methyls on here. The methyls are going to be on carbon 2, 3, 4, 5, 6, 7. So go to carbon 2, put a line. Carbon 3, line. Carbon 4, line. 5, 6, and 7. Each of those are methyl groups. And when you're done, you should have that. 2, 3, 4, 5, 6, 7, hexamethyl octane. Now again, on our exam, we're not going to do organic naming. You can wait for that. But you should understand the basic, especially the basic rules, be able to look at something and tell me what the longest chain is, et cetera, et cetera. Nice, simple things like that.
So the ethyl is always gonna be that curved line.
Ethyl is always going to be 2 carbons, so a vertex and an end. All right. A little bit earlier, we talked about conformational isomers. We said that everything spins around really quickly, and I said that we could ignore it because they're all identical. This is just kind of like a truth check. No, they're not exactly identical. If you look at ethane, ethane has 2 carbons and 6 hydrogens. Looks like this. We can rotate around this single bond here, as this is doing. And as it rotates, we can identify 2 major structures. Here, the hydrogens are in each other's face, aren't they? They are. And here, they're not. This is called eclipsed and staggered. And you can see it as it goes around here. When this gets here, that's all the hydrogens are basically touching each other. That's a higher energy situation. We can actually measure that. And as this thing rotates, we can measure the energy difference in the conformation. And it's about 12 kilojoules, which isn't much. The bottom line is that yes, they are all different structures. Yes, they do interconvert very, very rapidly. No, we really can't tell the difference unless we really look at it. But you can, because they are slightly different basic energies. All right, those are conformational isomers. This is something we actually can measure and tell the difference. These are called constitutional isomers. Look at these 2 guys. Where are the main chains here? In this guy, we have a 1, 2, 3, 4, 5 carbon chain, right? And we have an ethyl group here on carbon 3. Here we have a 1, 2, 3, 4, 5, 6 carbon chain with a methyl group, again, on carbon 3. Nonetheless, if you look at the formulas, this is C7H16. This is also C7H16. Nonetheless, these are totally different compounds. Totally different. Different melting point, different boiling point, different everything. But they have the same formula. These, once again, are called constitutional isomers. Now, here's a cute game that you can do. I can give you a formula and say, write all the constitutional isomers for C3H8. See if you can write one. 3 carbons, 8 hydrogens, draw me a structure. Now, if you only have 3 hydrogens, to be honest, there's only one way you can connect them, right? Zigzag, up and down, zoop, zoop, like that. That's the only way you can connect them. And the only constitutional isomer you can draw is propane. 1, 2, 3 carbons, 8 hydrogens. The only one. All right, what if I said instead to do C3H6? 3 carbons, only 6 hydrogens. Now remember, carbon can form double and triple bonds, also form rings. 3 carbons, 6 hydrogens. You could draw a couple for these. Go ahead, you could do this. Yeah.
I wanted to see the lineage. So that would just be.
Yep. Just the zigzag up and down.
Okay, so that last one you did,
Uh-huh.
that curve is it can't be CH3, CH3, CH2, because the curve, the point is the CH2. Right?
This is the
The middle.
CH2 in the middle. It's
Middle.
called the vertex. It's CH2.
So,
All right, so if we have C3H6, there are 2 ways you can draw this. We could take our 3 carbons and make a triangle. And that means that every carbon would get 2 hydrogens. We could also put a double bond in. The 2 look like this. This is called cyclopropane, 3 carbons in a ring. And this is a propene, 1 double bond, and then a CH3. Carbons, 1, 2, 3, 1, 2, 3, hydrogens, 2, 4, 6, 1, 2, 3, 4, 5, 6.
do you have to have those 2 symbols, or
Hmm?
if you draw the triangle by itself?
That would be correct.
So that would be CH2, CH2, CH2. Right?
How about if we did C4H8? Go ahead and draw me a C4H8. There are actually 5 of these. So think double bonds, think rings. Well, if n is 4, right? 2n plus 2 would be 10. So we must have a ring or a double bond in there somewhere. We're missing 2 hydrogens. This is the set. We can put 4 in a square. We can make our cyclopropane with a methyl group on it. Or we can make these all with 1 double bond. Now look at this, make sure you understand. 4 carbons, 1, 2, 3, 4. And each of these guys is a CH2. Here we have 1, 2, 3, 4 carbons. That's a CH3. That's 1, 2, 3, 4, 5, 6, 7, 8. Yeah.
Now you probably already can guess what question I'm gonna ask, right? So for this double bond here, obviously they're all going to be the same compound, CH2, 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 right? I understand that there's a square and there's also a triangle with an extra compound, but why do you have a double compound on 3 examples above the other chain?
Oh, it doesn't matter. Again, the 4 carbon chain, we have CH3, that's 1, 2, 3, 4, 5, 6, 7, 8 hydrogens.
Right, but I'm asking why isn't the double bond connected? Continuously connected.
Well, it's carbons, it has to be in the chain. It has to be in the chain.
Well, that's what I'm saying, that's why I'm asking, why is it separated?
Oh, it's not separated, no, it's all part of the chain.
Can you explain those top ones? I don't get the
Okay.
correlation.
All right, in this guy, we have 4 carbons. 1, 2, 3, 4, right?
So 1, 2, And the middle is 4?
Yep, that's a carbon.
Okay.
Now, this one is a CH3, so that's 3 hydrogens. This is a CH3, 3 hydrogens. This carbon already has 4 bonds, so it has no more hydrogens, does it? And this one only has 2 bonds, so it's a CH2.
How do you know it only has 2?
3, 6, 7, 8.
Oh, that's...
This one, CH2, CH, CH2, CH3. That's 8. All right, let's just look at this one because this one's fun. In intro, I always say this is the one that's on the exam. Of course, it isn't. Remember, carbon compounds can include oxygens, nitrogens, and anything else that you want. This seems like a really simple molecule, doesn't it? C3H6O2. How many isomers do you think we can have? Well, let's start with these. And then let's add these.
Oh my God.
It's just amazing how complex carbon compounds can get so very quickly. All right, what is on the exam? Something like this. Here I give you 2 structures. Are these identical? Constitutional isomers or totally different compounds? Come on, you can do this one. That's exactly what you do. You count the carbons. And you're going to come up with a formula. This is 1, 2, 3, 4, 5 carbons.
I think...
And 12 hydrogens. How many in the next one?
C5.
1, 2, 3, 4, 5, 6 carbons. And 14 hydrogens. So these don't have the same formula, do they? So these guys are totally different chemical compounds and not isomers.
Or, that's
Yeah.
1, 2,
Say we have an exam, right, and we have to make a lineage for the chemical compound. Is it alright to make just a lineage on the first example? Maybe like the first example.
Right.
It would be either one.
These are different formulas. Remember to be isomers that must have the same formula. That's a simple way you just count.
So
Do one more. Look at these 2. Here's a line drawing, here's a condensed structure, sort of. Are these identical, isomeric, or different? Start off here with your longest chain. How many carbons in our longest chain? It's going to be 1, 2, 3, 4, 5, 6. 6 carbons. Look over here. How many carbons in your longest chain? 1, 2, 3, 4, 5, 6 carbons. So both chains have the same number of carbons, right? All right, now let's see, we have chlorines, don't we? If this was carbon 1, then the chlorine would be attached here to number 2. Okay? If this was carbon 1, the chlorine's attached to number 2. All right, this is 2, 3, and 4. Another chlorine and carbon 4. 2, 3, 4. Another chlorine and carbon 4. 6 carbon main chain, chlorines in 2 and 4. 6 carbon main chain, chlorines in 2 and 4. These are identical. Simply an exercise in reading the structures. All right. We've looked at things that have double bonds, not a triple bond yet, but let's just talk a little bit about why we draw double bonds and what that really means. This is a carbon-carbon double bond. This is called ethene, and we'll see that this is referred to as an alkene. Remember, alkanes ended in A and E. Alkenes are E and E, and that tells you it has a double bond. This is acetylene, also called ethyne, and the Y and E indicates it's an alkyne with a triple bond. Now, where does the double bond come from? Remember, we took an S and 3 p orbitals and made our tetrahedral hybrid. Well, if we take one S and only 2 p orbitals, then we wind up with 3 things bonded. So we have 3 orbitals, we can make 3 bonds. And it looks like this. Our bond angles are 120. But, keeping us honest, remember each of these carbons still has a p orbital left, doesn't it? Each of these still has a p, one that we didn't use. So let's draw it in there. Now, these p orbitals can line up. When they do, they share electrons. And this forms what we refer to as a pi bond. Kind of looks like a hot dog. Here's our structure in the middle with the electrons above and below it. This is what we refer to as our double bond. One bond comes from building these things together, and the other is from these p orbitals that overlap. When we write a double bond, what we mean is we have one real bond, and the second bond is actually this thing, the electron cloud that connects the 2 carbons. This is what it looks like. You can see the big wad of electrons here representing this cloud above and below. There's one other cute thing about this. In order for these things to overlap and form their little hot dog bond structure, they have to line up perfectly. And that means that you can't rotate around this single bond anymore. Because if you did, it would go like this, and they don't line up anymore. That means when you have a double bond in a molecule, you can have 2 more isomers. There's our double bond. We could say that our methyl groups here and here are on opposite sides of our double bond, because remember this doesn't rotate, or they're on the same side, trans and cis. Now I say that they don't interconvert because they can't, but in fact they do, of course. In fact, the chemistry of vision you have retinal in your retina. It's a long compound with lots of double bonds. They are cis double bonds. Light comes in, hits retinal, excites it, and when it does, it breaks this double bond, allows it to rotate, and you wind up with the trans isomer. That changes the shape of the molecule. Your brain interprets that as, oh, a photon just hit my retina. That's how vision works. Simple cis trans isomerization. We refer to these guys as stereoisomers because they only differ in the way they're organized in space. Again, stereoisomerism is a big thing in organic. Let's look at our sp center real quickly. Here we're going to take two orbitals. We're going to combine these. We make a linear structure. Now, just like before, we had p orbitals left over. P orbitals, one's up, one's sideways. They do like that. And so we get two pi bonds formed. One this way, one that way. In reality, they all combine into one big mess surrounding the two carbons. One real, two pi bonds, and it looks like that. All right, one more little topic here, because we need to introduce the concept of functional groups in order to move into biochemistry. Remember we talked about functional groups a little bit. Functional groups are interesting in organic chemistry because all of the compounds will have very similar reactivity. We've had single bonds, double bonds, triple bonds. The functional groups for these are alkanes, alkenes, and alkynes. Now we're just going to quickly run through a bunch of functional groups that are representative, and I'll point out the ones we need for biochemistry. These are just examples, first of all. If we have a double bond, we'll call this an alkene. An OH would be an alcohol. An oxygen bonded to two carbons would be an ether. This is an example of what I mean about reactivity. If we have a molecule that's an alkene, it will react with bromine, and it will form a dibromide where the bromines are on opposite or on adjacent carbons, and they're opposite to each other. We say that's trans. One of the great things we do in organic chemistry is to look at the mechanism, exactly why and how this happens. This is cyclopentene, here's our double bond, and this represents bromine. In organic chemistry, we use lots of arrows to show the flow of electrons. Electrons flow from our pi system up here, and we form what's called a bromonium ion, intermediate. Very short lifetime. We also release Br minus. Br minus down here will now attack this carbon, breaks that ring, and we get the 1,2 dibromide, and they're on opposite sides. Called an organic mechanism. One of the joys of organic chemistry is you get to learn lots and lots and lots of functional group reactions. Just for example, for a simple alkene, these are the ones that we typically go over. All right, let's just quickly run through our functional groups. We've done alkane, alkene, alkyne. This is a benzene ring. Perhaps you've heard about benzene. Used to be a wonderful solvent, still is. Used to be ubiquitous. It was in everything. It was even in Perrier drinking water. All of these double bonds here, these carbons all have the 1p orbital left over, don't they? So this really looks like this. All of these overlap to form an incredibly stable pi system. Looks something like that. Benzene is one of the really important compounds in organic. If we attach a halogen, we call it a halide. OH is an alcohol. We did the bridging, that's an ether. This one you should know for biochemistry. If we put an amino group, an NH2 for example, that's called an amine. Triple bond nitrogen is a nitrile. You can put a nitro group on. SH. SH is also important in amino acids, called a thiol. S in the middle is a sulfide. Carbonyls, carbon-oxygen double bond. Very important class of compounds. Aldehyde, one hydrogen, ketone, no hydrogens. Carboxylic acid, this is the acidic group right here. Amide, if we put a nitrogen on one side of our carbonyl, it's called an amide. Now, why are carbonyls so important? Because they're very reactive. Remember we talked about electronegativity? Oxygen is electronegative, carbon is not. And it sucks the electrons up towards itself. That means something with electrons, I'll just use methanol here, can attack this carbon. When it does, these electrons move up, pick up a hydrogen, give us an intermediate, and this breaks down. This is the functional group called an ester. Again, this is the heart of organic chemistry. It's mechanisms, reactions, reactivity. Now I said we would look at these in biochemistry. Biochemists, biomolecules, most biomolecules are either made of amino acids or derived from them or something like that. Amino acids, we just looked at this. This is a carbonyl with an OH. That's an acid group, isn't it? And here on the next carbon, we have an amino group. So this is an amino acid. All of these are our 20 essential amino acids. And you'll note that they all have the amino acid top, but they have different bottoms. These are different side chains. So these guys are positively charged. These are negatively charged. These guys are polar, but they're not charged. An alcohol, another amide, another amide. Here's the sulfhydryl I talked about, SH. You could even do selenium. This one just has hydrogens. And these guys are not water soluble. So here we have a methyl group. Here we have a branched side chain, a longer side chain, another branched, a benzene ring. These guys are all water insoluble. The solubility characteristics of the amino acid side chain are what make proteins adopt their shape. Let's take two amino acids. Okay? So in your body, you have amino acids. To make a protein, you need to take amino acids and put them together. What we're going to do is take the acid group here, the amino group here, and we're going to link them. This nitrogen is going to come bonded here. When it does, we're going to lose an OH and an H. That's water. So watch the magic. The water goes up, and we form an amide. The amide is the backbone of a protein. This is now another amino group, isn't it? It can react with another acid group, can't it? These are the amino acids: leucine, glycine, serine, and alanine. When you just have a few like this stuck together, we call that a peptide. If you take a lot and stick it together, you get a protein. Again, these are all just individual amino acids linked up just like we saw. The amino group and the carboxylic acid.
So when protein gets broken down by your body, they
You
break
go
down to amino acids,
all the way
right?
back down to amino acids, right? This is the enzyme lysozyme. The little coils you see here are called alpha helices. An alpha helix is formed when you have side chains that are very water soluble. So they want to get out in the water. Forces the amide backbone to spiral up like that. This is called a beta turn right here. In the beta turn, they pair up going backwards. There's another little turn, whatever. In an enzyme, because all of these groups impart this specific geometry to this chain, specific, they all look like this, you wind up with little cavities and stuff like that. And that's where you bind, this is what it looks like as a 3D model. Can't really see much here, but you can see all of the blue, those are polar groups sticking out, and all the non-polars are in the middle. And your substrate will come sit in the hole, and then it will do its magic catalysis. Now the other biomolecule we want to talk about are DNA and RNA. They both have 5-carbon sugar backbones. They differ because this one in carbon 2 has a hydrogen. Over here in RNA we have a hydroxyl group. So this is deoxyribose and ribose. This goes in DNA and this goes in RNA. What we do is link this deoxyglucose to a base. This is purines, so there are 2 rings fused together, guanine and adenine. The other pair of bases look like this. They're 6-membered rings, cytosine, thymine, and if we're dealing with RNA, we get uracil. What you do is you form basically a polymer among the ribose here, ribose and phosphate, and then the bases pair up depending on hydrogen bonding. And we saw this very same slide when we did hydrogen bonding. Here we have an NH and an oxygen. Here we have an NH and a nitrogen. And here we have an NH and another oxygen. These 3 hydrogen bonds tell the cytosine that it's properly paired with a guanine. We put these all together. We have our ribose phosphate backbones on both sides. And here we have our hydrogen bonds between our things, linking them all together. Here we have bases. You can see the bases lined up nicely. The solid line on the outside represents the phosphate backbone. Now, in just a minute, this is going to change. I forget what it changes to. But you can see how they're all lined up nicely, hydrogen bonding. There we go. Now here you can see the phosphate ribose backbone on the outside. And here are these guys all hydrogen bonded in the middle. Here's all bases. You can see them bonding each other. And then I think there's a nice view there. There. Again, you can see in the ball and stick, here's our bases lining up, and the phospholipase on the outside. The final biomolecule we want to talk about is fat and lipid. All familiar with that? This is a fatty acid. There's our double bond. What's our geometry here? Both on the same side, it's a cis, right? Whenever you see an ad or something and it says something about trans fat, that's the trans isomer. The difference is, your body can eat this for lunch. It's a wonderful food. The trans can't touch. Doesn't fit, doesn't work. That's why it just sits there and goes to your hips. And stays there forever. Multiple double bonds are polyunsaturated fats. The fats that you should eat will have lots of double bonds or none. None is called a saturated fat. They used to be vilified because they were going to make you fat. We'll see in the chapter on food, they don't.
So the trans fat never leaves?
Hmm?
The trans fats, they never leave your body?
Nope.
Oh, wow.
Yep, don't want to do that. If we take 3 fatty acids of some sort, any sort, hook them to a polyalcohol by ester linkages, this is called a triglyceride. This is the way fats are stored in the body. They form these big lumps of fats. These can be clipped off easily, though, free fatty acids, if you ever need to metabolize fat. Membranes. Everything in the body is separated by membranes, right? Membranes are made up as a derivative of this. This is a phospholipid. So again, we have long fatty acids. But here we have a very polar group. This is a choline out here. What happens in the body, and actually everywhere, is that all of these non-polar tails will line up with the polar ends sticking out into the water. And you wind up with a bilayer like this, where all of these polar ends, non-polar ends, are stuck together. All of the polar ends here are on the outside, and this is the membrane structure that separates everything in cells. It makes up the cell membrane, etc., etc. Finally, you can't talk about fats without talking about cholesterol. This is cholesterol. Now we know a little bit about chemistry now. We can look and see this is an alcohol, isn't it? 6-membered ring, here's a double bond in a 6-membered ring. Another 6, here's a 5, and here's a side chain sticking out. This is cholesterol. It's a beautiful molecule. it actually looks like this, very planar, and this is its side chain. Very slightly polar on this end, very, very nonpolar on this end. Now, cholesterol, speaking of being vilified, is the one that has really taken the hit for many, many, many years. It got the worst during the 50s with Eisenhower, because Eisenhower had really bad heart problems, okay? And they did surgery and stuff like that. And when they did, they saw something very unappetizing, like this. This is actually a model, but of a plaque, an arterial plaque. Now, the artery is supposed to end here with this little red muscular layer and its little membrane around it. But in a plaque, you have the buildup of these big, fat, ugly, fatty cells. And they build up and up and up and up and up, and eventually cut off the blood flow. So, what they did is they said, hey, that's bad, okay? And they analyzed what's in here. Well, these are fats, there's some protein, and there's a whole lot of cholesterol. And so they told everybody, starting in the 50s, don't eat cholesterol, don't eat fat. Now, scientifically, it makes no sense at all. And he knew that at the time. But it makes no sense at all. Why? Because most of the cholesterol in your body, most of it, is made by your liver and your intestines. Like 75–80% of it. You make it because you need it. You use it all the time. You get just a tiny bit from something you eat. And fats, as we'll see in the chapter on food, fats are actually a wonderful food. Fats don't make you fat. In 2015, USDA finally came out and said that their guidelines saying that you must limit cholesterol intake should be repealed. So that's just last year. They finally admitted it since the 50s. Limiting cholesterol does not correlate with lower blood cholesterol because you make most of it yourself.
So whoever has like a bad cholesterol, high cholesterol.
Well, that's different. Cholesterol circulates in your blood. It circulates bound to a protein. These are called lipoproteins. They are basically categorized into two groups: high-density lipoproteins and low-density lipoproteins. High-density lipoproteins are what they refer to as bad cholesterol. If you have lots and lots of that, it's a bad thing. Low-density lipoproteins are good cholesterol. But changing your diet doesn't have any effect on that ratio.
So I take medication.
Yeah, pretty much.
So how do you avoid high cholesterol then?
Well, you have to pick your genes very well.
No
Okay.
way. So if my family is propense to have high cholesterol, then the percentage increases with.
Yeah, and it's probably.
And there's nothing we can do?
And well, yeah, you can take statins and stuff like that. Those work very nicely. But the point here is that if you stop eating eggs because they're high in cholesterol, doesn't do anything at all. Eggs are perhaps the perfect food. Well, that's
Are they
good.
supposed to be high protein?
Yep, high protein, high fat, high cholesterol. Perfect food.
So when they say avocados has good fat, what does that mean?
It has avocados and other great fruit.
So
It has lots of good fats, lots of polyunsaturated
Might as well
fats,
eat
saturated fats, no trans fats. It's a
The
great.
trans
good
fats are
food.
mostly from processed foods.
All right, so that's organic and bio as an intro. Like I said, next week we will have exam review, and then the week after that we'll do an exam. So sometime between now and then I will come up with a sample exam and get it to you somehow. All right, are we good? Yeah.
Which chapter is it?
So that's that, for example, you have to,
5, 6, 7,
5, 6, 7, 9, right?
you have to complete the exam, bring it to class like the last time, or?
Yeah.
Oh,
Yep, just like last time.
and finish the tutorials before the exam.
Yep.
Great.